Hey everybody, Daniel here from Basement Tech. Well, you can guess by the fact that I'm sitting at the computer with datasheets open and sketchbook out that something must be going on with the CNC router controller build. Well, this is one I kind of saw coming, but was just avoiding thinking about. And let's maybe start here, and that'll sum up the challenge. These are the inductive sensors that came with the mill itself. They were all mounted, really nice semi-commercial mounts and wiring and everything. You can see the output range, the operating voltage range is 10 to 30 volts. The prior owner had them running at 12 volts. This is the input specification for the breakout boards that I'm using from CNC 4PC. No knock to either, it's just the operating voltages are different. You can see the input voltage is 2 to 5 volts. Now, having said that, as I scroll down here to the bottom and find the CNC 4PC manual section that deals with this, we can start to talk about what kind of solutions we have. Now, this is a really nice manual, by the way, from CNC 4PC on the C10 breakout board, and I presume all of their manuals are like this, so kudos to them. So they provide these functional block diagrams, which give me an idea of the equivalent circuit for inputs into their device. If I continue to slide down, they even take it one step farther and say, hey, if you're using NPN sensors, which I am. This inductive sensor is actually like a NPN transistor on the inside, an open collector input. How do you wire that? So that's the place to start here, and it was a good place to start, but even with that help, I ran into a little challenge. Now, I have to admit, this video is going to be a little more technical than usual, and I will say right up front, there probably are other solutions than the one I propose here. Like everybody says, you know, if you have a screwdriver, everything looks like a screw. In my case, I know how to do engineering and I have boxes of parts, so I brought those to bear on this problem. I have to imagine there must be breakout boards that can accept 12 volts directly in. And like I said, other solutions. This happened to be the one I came up with the parts I have available in my junk box. So let's talk about that. Okay, so not only did the CNC 4PC people talk generically about NPN open collector sensor inputs, but they actually talk specifically about ones that have an internal pull-up resistor. The inductive sensor was behaving as if it did have one, so I sent an email off to the makers of that sensor and asked, does it in fact have an internal pull-up? They said yes, but they were unable to provide me with the value, which makes me feel like they're more of a distributor than an actual manufacturer, which was okay. That's okay. It confirmed my understanding that there was in fact an internal pull-up. And again, CNC 4PC anticipated this and provided some instructions. I'm going to skip over some details and jump right to this picture. It turns out that the internal pull-up resistor and output equivalent circuit on the inductive sensor looks a little bit like this, and it has a 33K sort of internal pull-up resistor, which means that the solution provided by CNC 4PC isn't really useful. They anticipate a lower value, which means that more of the voltage would be dropped across a series resistor, shown kind of in the background here in R2, and that's a bit of a problem. The size of this resistor means that almost anything I put in here would result in most of the voltage being dropped across the 33K internal. And you might remember this breakout board gives me a really nice option, to either pull up or pull down the input with a 4.7K. Now, again, the CNC 4PC documentation says pull it down, and then you put another resistor in series, and you have a nice voltage divider. But given the size of this, all of the voltage is dropped here, and doesn't leave me with a nice, robust signal. The kind of robust signal that I want for this build. Since I've been babbling on, let me just jump to the solution. I immediately thought, well, a little circuit with a MOSFET. MOSFETs have very high input impedance, and and the gate is more or less isolated from the other circuit. So you can have one voltage on the gate voltage and another voltage on the drain voltage. So you can see this little circuit down here. That's what I ended up with. Again, I have these parts on hand. I can sketch out these kind of things and figure them out. So that's why I went in this direction. There probably is a off-the-shelf breakout board with 12-volt inputs, or there probably are sensors which can go down to 5 volts. So it's a MOSFET here essentially, and if you know anything about transistors, the gate, or in the case of a bipolar transistor, the base controls the flow of electricity on the output side of the transistor, if you will. In this case, I was able to use the pull up 4.7K, pulled up to 5 volts, and then with the external resistor, a high value external resistor, and a very high impedance here, I can get about 8.62 volts on the gate, which turns this transistor on very robustly and provides me a great 5-volt signal out here. You can see the specs down here. This is a pretty good transistor, probably overkill, but I had a whole bag of about 50 of them. It's the ZVN 4306A. To be remarked upon is this great R-on resistance. It acts almost like a short circuit, much better than a bipolar, and this 8.62 volts will provide a very robust turn-on, so we'll be achieving something in that range of on resistance. And then finally, I debated heavily about this resistor here. Given that this is a very high input impedance, I could have probably done without it, but most MOSFET circuits have some kind of resistance to drain the charge off the gate, and it provided a predictable, very stable voltage here instead of kind of leaving it up to random impedances. All right, so sorry, lots of electrical engineering and stuff for those who care. For those who don't, just skip over this video and I'll show you the final product here in a minute. The second step in these kinds of things is to prototype up the circuit that you've designed on paper and make sure it actually does what you want it to do. Common way to do that is using this little device called a breadboard. It allows you to plug in components and try out circuits, variations of circuits really quickly. So I've done that here with our circuit that I showed you on paper earlier. The yellow wire comes from the connector over here, and I have an actual one of the limit switches wired in through that little circuit. And the test here is just to make sure this signal makes it through the transistor into the breakout board, from the breakout board into the smooth stepper, through the Ethernet, and all the way back to Mach 3. I configured up a really simple input here on the signal called input 1. I just randomly chose that as a test. You see that configured somewhere. There you go. Input 1 is on port 2, pin 9, where I've wired the output of the transistor circuit. So I'll just close that up. And if I take this proximity sensor and get it close to metal, that metal object, you can see it triggers. The little LED on the inside is triggering. But is that signal making it all the way through? Well, let's take a look at this diagnostic screen in Mach 3. Remember, I tied it to input 1. And lo and behold, yes, it's making it all the way through the chain, and that gives me confidence that my limit signals will also make it all the way through the chain. So I do this kind of construction typically with some kind of a proto board. Again, as I've said a lot of times to you guys, I look in my junk box and see what I have. This is a pretty neat one. I'm going to solder these components onto this board, so you can see this kind of proto board provides these copper tracks that run in different directions to make it easy to make the connections that we need in order to build up that schematic diagram in physical form. Most of the parts here, I had these transistors like I mentioned earlier, and the terminal block are just from the junk box. This is going to work out well. I'll show you when it's all done. Here you are, the finished 12 volt to 5 volt converter circuit. Very simple. The next time you see this, it'll be mounted in the big box and doing its job. The blue wires are going to go out to the breakout board, and the wires from the connectors that are used on the limit switches will come in here. Oh, there's the little board all mounted in its place. Since I started the video, I actually got all the wiring, internal wiring done, which is pretty exciting. So you can see the yellow wires coming from the connectors and these blue wires coming out and going into those breakout board. The breakout board inputs where I have them jumpered high and set for inputs. This turned out really pretty cool. I'm pretty excited. You can see all of the holes in our connector panel are all filled in. The motor outputs here on the right and the limit switches there on the left. The bottom 6 are the ones connected to that new voltage converter board. The top 2 go straight to the breakout board. And then the Ethernet input for the smooth stepper. And kind of coming around to this side, you can see lots of wires, including the spare DB9 there. And then these heavier wires are the motor outputs from the controllers, which go over to the back side of those DB9s. I think we're getting really close to deploying this thing, so maybe that'll be hopefully the next video. If you like this video, give it a thumbs up. If you really like, punch the subscribe button, and if you really like it, ask for notification when new videos appear.